Langchain XR retrievers. Description: Langchain XR retrievers are a powerful tool for building advanced information retrieval systems. They leverage the capabilities of Langchain, a framework for building applications powered by large language models (LLMs), to enhance retrieval efficiency and accuracy. XR retrievers offer a unique approach to retrieval by integrating external data sources with Langchain's functionality, allowing you to access and process data beyond the limitations of traditional retrieval methods. Inputs. Document collection. The input consists of a set of documents, text, code, or other forms of data that you want to use for retrieval. These documents can be stored in various formats, such as text files, databases, or even directly from the web. Query. The query is a user input, a natural language question or a structured request that represents what the user is looking for within the document collection. Outputs. Relevant documents. The output is a ranked list of documents from the collection that are most relevant to the user's query. The ranking is based on the retriever's ability to assess the semantic similarity between the query and the content of each document. Retrieval scores along with the relevant documents. XR retrievers often provide retrieval scores, which quantify the relevance of each document to the query. These scores can be used to further refine the ranking or provide insights into the strength of matches. Steps. Data preprocessing. Documents in the collection are preprocessed, potentially including tokenization, stemming, and stop word removal, to prepare them for efficient comparison with queries. Query embedding. The input query is transformed into a vector representation using a suitable embedding model. This vector encapsulates the semantic meaning of the query. Document embedding. Each document in the collection is also converted into a vector representation using the same embedding model. Similarity calculation. The query embedding is compared to the document embeddings using a similarity metric, e.g., cosine similarity. Documents with higher similarity scores are considered more relevant. Ranking. The documents are ranked based on their similarity scores, with the highest scoring documents appearing first in the output. Metrics. Retrieval accuracy. This metric measures the effectiveness of the retriever in retrieving relevant documents. It can be assessed using various methods, such as precision, recall, and F1 score, which consider the number of true positives, false positives, and false negatives. Retrieval efficiency. This metric evaluates the speed and computational cost of the retrieval process. Factors like query processing time and document retrieval speed contribute to efficiency. Visualization plots. Retrieval ranking visualization. This plot can show the ranked list of retrieved documents, visually highlighting the relevance scores for each document. Retrieval time analysis. This plot can showcase the time taken for retrieval, potentially comparing different retrievers or variations in query complexity. Fine-tune parameters. Embedding model. The choice of embedding model, e.g., sentence transformers, OpenAI embedding, significantly impacts the quality of retrieval. Fine-tuning the embedding model with specific domain knowledge can improve accuracy. Similarity metric. Optimizing the similarity metric, e.g., cosine similarity, Euclidean distance, can refine the ranking based on the desired behavior. Uncertainty methods. Confidence scores. XR retrievers can incorporate confidence scores to indicate the retriever's certainty about the relevance of each retrieved document. Higher confidence scores suggest stronger matches. Diversity measures. To promote retrieval of a diverse set of documents, methods can be employed to assess the diversity of the retrieved document set. This ensures a broader perspective on the query. Challenges and fixes. Challenge 1: Retrieval bias. Retrieved documents might exhibit bias towards certain topics or perspectives, influenced by the embedding model's training data or the nature of the document collection. Sample use case that resulted in Challenge 1: when retrieving documents related to climate change. The retriever might disproportionately return articles from a specific political viewpoint due to bias in the embedding model. Fixes to Challenge 1: utilize the biasing techniques for embedding models or curate a balanced document collection to mitigate bias in retrieval results. Challenge 2: limited contextual understanding. Retrievers might struggle to grasp complex queries that require contextual understanding or reasoning. Sample use case that resulted in Challenge 2: a query like explain the difference between quantum computing and classical computing might result in less relevant documents if the retriever lacks the ability to understand the nuances of the concepts. Fixes to Challenge 2: employ techniques like query expansion or integrate additional knowledge sources to enhance contextual understanding. Consider using more sophisticated embedding models capable of capturing complex semantic relationships. Challenge 3: scalability. Handling large document collections can pose challenges for retrieval speed and efficiency. Sample use case that resulted in Challenge 3: retrieving documents from a massive database of scientific articles might take an unacceptable amount of time using standard methods. Fixes to Challenge 3: explore techniques like approximate nearest neighbor search and to efficiently handle large datasets. Consider utilizing specialized hardware or distributed retrieval architectures to improve scalability. Langchain XR retrievers. ExaSearch retriever. Description: the ExaSearch retriever is a Langchain retriever that leverages the ExaSearch engine for efficient and scalable retrieval of relevant documents from a large corpus. ExaSearch is a vector search engine designed for high-performance retrieval, particularly for large datasets. Inputs: ExaSearch connection. A configured connection to an ExaSearch instance. This connection specifies the server address, port, and authentication credentials if required. Index name: the name of the index within ExaSearch that holds the documents to be retrieved. This index should have been previously created and populated with the documents. Query: the text query that describes the information being sought. This query is used to search for relevant documents within the index. Top K: the number of top-ranked documents to retrieve. This parameter controls the number of results returned by the retriever. Outputs: retrieved documents. A list of documents that are ranked by relevance to the query. Each document is represented as a dictionary containing information such as the document ID, the content, and potentially other metadata. Steps: query embedding. The query is embedded into a numerical representation using a pre-trained embedding model. This embedding captures the meaning of the query. Similarity search: the query embedding is used to search for similar embeddings within a ExaSearch index. ExaSearch uses efficient vector search algorithms to find the closest matches to the query. Embedding: document retrieval. The documents associated with the closest embeddings are retrieved from a index and returned to the user. Metrics: retrieval accuracy. This metric measures how well the retrieved documents align with the user's intent as represented by the query. It can be assessed using metrics like precision, recall, and F1 score. Retrieval speed: this metric measures the time taken to retrieve documents for a given query. It reflects the efficiency of the search process and the performance of ExaSearch. Visualization plots. Relevance ranking plot. This plot visualizes the retrieved documents in terms of their relevance scores. It allows users to understand the distribution of relevance scores and identify the top-ranked documents. Document Similarity Heat Map. This heat map visualizes the similarity between the query embedding and the document embeddings. It provides insights into the relationships between documents and the query. Fine-tune parameters. Embedding model. This parameter allows users to select the pre-trained embedding model used for query embedding. Choosing a model appropriate for the specific domain and language of the documents is crucial for accurate retrieval. Index configuration. The ExaSearch index configuration can be adjusted to optimize retrieval performance. This includes parameters like the index size, the number of dimensions for the embeddings, and the search algorithms used. Uncertainty methods. Confidence score. ExaSearch can provide a confidence score for each retrieved document, indicating the likelihood of it being relevant to the query. This score can be used to assess the uncertainty associated with retrieval results. Challenges and fixes. Challenge 1. Cold start. When retrieving from a newly created index or a sparsely populated index, there may be insufficient data for accurate retrieval. Sample use case that resulted in Challenge 1. A user queries a newly created index with a few documents, and the retrieved results are not very relevant. Fixes to Challenge 1. Populate index. Ensure the index is populated with a sufficient number of documents representing the domain of interest. Use seed documents. Add a few seed documents that are known to be relevant to the query topic. These documents can act as starting points for retrieval. Challenge 2. Query complexity. Complex or ambiguous queries can lead to less accurate retrieval results. Sample use case that resulted in Challenge 2. A user queries for information about the history of artificial intelligence, which is a broad and ambiguous topic. Fixes to Challenge 2. Query refinement. Encourage users to refine their queries by providing more specific keywords or using synonyms. Query expansion. Use techniques like keyword expansion or semantic search to broaden the scope of the query and retrieve more relevant documents. Challenge 3. Scalability. Retrieving from large indices can become computationally expensive and time-consuming. Sample use case that resulted in Challenge 3. An organization tries to retrieve documents from an index containing millions of documents, and the retrieval process becomes slow. Fixes to Challenge 3. ExaSearch optimization. Optimize the ExaSearch index and configuration for efficient retrieval from large datasets. Distributed retrieval. Consider using distributed retrieval systems like ExaSearch's distributed search capabilities to handle large-scale retrieval tasks. Langchain Exa tools. Description. Langchain Exa tools are a suite of tools designed to enhance the capabilities of Langchain, a popular framework for building large language model applications. These tools offer a wide range of functionalities, from data exploration and analysis to model fine-tuning and uncertainty quantification. Input 1. Raw data in various formats: text, JSON, CSV, etc. that can be processed and analyzed by Langchain. Input 2. User prompts and instructions that specify the desired tasks and outputs from the Langchain models. Output 1. Processed data, insights, and results generated by Langchain based on the provided inputs. Output 2. Summarized information, visualizations, and reports that facilitate understanding and decision-making. Step 1. Data ingestion and preprocessing. Data is imported, cleaned, and transformed into a format suitable for Langchain processing. Step 2. Model selection and execution. An appropriate Langchain model is chosen based on the task at hand, and the model is run on the prepared data. Step 3: Output generation and interpretation. The model's output is analyzed, interpreted, and presented in a meaningful way to users. Metric 1: Accuracy measures the correctness and reliability of the model's predictions or outputs. Metric 2: Precision indicates the proportion of correct predictions made by the model. Metric 3: Recall represents the proportion of relevant instances that are correctly identified by the model. Metric 4: F1 Score, a harmonic mean of precision and recall, providing a balanced measure of model performance. Visualization Plot 1: Scatter plots visualize relationships between variables in the dataset. Visualization Plot 2: Bar charts represent categorical data and compare different groups. Visualization Plot 3: Line charts show trends and patterns over time or continuous variables. Visualization Plot 4: Histograms display the distribution of data and identify outliers. Parameter 1: Learning rate controls the step size during model training. Parameter 2: Number of epochs determines the number of times the training data is iterated through. Parameter 3: Batch size specifies the number of data points used in each training iteration. Parameter 4: Regularization parameters help prevent overfitting by penalizing complex models. Uncertainty Method 1: Monte Carlo dropout uses random dropout during inference to estimate model uncertainty. Uncertainty Method 2: Bayesian deep learning introduces prior distributions over model parameters to capture uncertainty. Uncertainty Method 3: Ensemble methods combine multiple models to reduce variance and provide uncertainty estimates. Challenge 1: Data quality. Poor data quality can lead to inaccurate model predictions and unreliable results. Sample use case that resulted in Challenge 1: A dataset with missing values or inconsistencies might result in biased or inaccurate analysis. Fixes to Challenge 1: Data cleaning and preprocessing techniques can be used to address data quality issues, such as imputation of missing values and correction of errors. Challenge 2: Model selection. Choosing the right Langchain model for a specific task is crucial for achieving optimal performance. Sample use case that resulted in Challenge 2: Using a model designed for text generation for a task that requires classification might lead to subpar results. Fixes to Challenge 2: A thorough understanding of different Langchain models and their strengths and weaknesses is essential for making informed selection decisions. Challenge 3: Overfitting. Models can overfit to the training data, leading to poor generalization performance on unseen data. Sample use case that resulted in Challenge 3: A model trained on a small dataset might memorize the training examples instead of learning general patterns. Fixes to Challenge 3: Regularization techniques. Cross-validation and early stopping can be used to mitigate overfitting. Challenge 4: Interpretability. Understanding the reasoning behind model predictions is essential for trust and accountability. Sample use case that resulted in Challenge 4: A black box model that provides accurate predictions without providing insight into its decision-making process may be difficult to trust. Fixes to Challenge 4: Methods like attention mechanisms, saliency maps, and feature importance analysis can help to interpret model predictions. Challenge 5: Scalability. Handling large datasets and complex tasks requires efficient and scalable solutions. Sample use case that resulted in Challenge 5: Training a large language model on a massive dataset can be computationally expensive and time-consuming. Fixes to Challenge 5: Distributed computing frameworks, efficient data storage and retrieval techniques, and model parallelization can address scalability challenges. YAML. Langchain EXA tools EXA search results. Description: explain in detail. The EXA search results tool allows you to retrieve and process results from EXA. EXA is a platform that allows you to run your own language models (LLMs) on your data in a secure and scalable way. Inputs. Input 1. Explain in detail query: the query that you want to run on your data. This can be a natural language question or a structured query. Input 2. Explain in detail EXA instance: the EXA instance that you want to connect to. This contains your data and the LLMs that you want to use. Outputs. Output 1. Explain in detail results: a list of documents that are relevant to your query. Output 2. Explain in detail metadata: metadata about the results, such as the number of documents retrieved, the time it took to retrieve the results, and the confidence score for each document. Steps. Step 1. Explain in detail connect to the EXA instance. Step 2. Explain in detail run the query against the data. Step 3. Explain in detail retrieve the results. Metrics. Metric 1. Explain in detail number of documents retrieved. Metric 2. Explain in detail time it took to retrieve the results. Metric 3. Explain in detail confidence score for each document. Visualization plots. Visualization plot 1. Explain in detail scatter plot of confidence score vs. document rank. Visualization plot 2. Explain in detail histogram of confidence scores. Fine-tune parameters. Parameter 1. Explain in detail query: the query used for search. Parameter 2. Explain in detail filters: any additional filters applied to the search. Parameter 3. Explain in detail ranking: the ranking algorithm used to sort the results. Uncertainty methods. Uncertainty method 1. Explain in detail confidence scores: a numerical measure of the model's confidence in the relevance of each document. Uncertainty method 2. Explain in detail diversity ranking: a ranking method that prioritizes diverse results over high confidence results. Challenges and fixes. Challenge 1. Explain in detail: the EXA instance may be unavailable. Sample use case that resulted in challenge 1: the EXA instance may be down for maintenance, or it may be experiencing a network outage. Fixes to challenge 1: retry the connection to the EXA instance. If the problem persists, contact EXA support. Challenge 2. Explain in detail: the query may be too broad or too narrow. Sample use case that resulted in challenge 2: a query that is too broad may retrieve too many results, while a query that is too narrow may retrieve too few results. Fixes to challenge 2: refine the query to be more specific or more general. Challenge 3. Explain in detail: the data may be incomplete or inaccurate. Sample use case that resulted in challenge 3: the data may be missing information, or it may contain errors. Fixes to challenge 3. Contact the data owner to request updates or corrections.